We're playing with growth models, and we looked at a couple of different kinds of models and a couple of different ways to write them down mathematically. All right, so let's take a look at first, we'll review the linear models. And linear models could either be recursive or explicit. Recursive means step by step. Explicit means I immediately get to any point in the list. So example of recursive would be something like start at 1, and then to get some other term, the other term we just call a sub n, a with an n by it, we could do something like add 3 to the previous term. And does anybody remember what the subscript for the previous term is? It's the n minus 1, yeah. So all that just means is whatever the previous term is. So to generate a list based on that of n's and the a's, here it says to start with 1, and then this basically says add 3 to the previous term. So if I want to get the second term, the previous term is 1, and so I need to add 3 to get 4. To get the third term, so n is 3, the previous term, n minus 1 would be 2, I just add 3 to that previous term. And then I can keep generating that list of numbers. So all the recursive says is, give me a place to start, what do I do to the previous term to keep going? Turns out spreadsheets have the basic tools to do recursive formulas really easy. And so if I were going to make a list here, I could say start at 1. So I just type my 1, enter. And then I want to feed my spreadsheet this part of the formula next. So to do that, I would just, if I want to do a calculation, what do I have to type first? Remember, we type equals first, right? And then I want to take 3 and add it to the previous term. How do I tell the spreadsheet to get the previous term? You click on the previous term, yeah, so I just go click, that's the previous term, and it says, oh, you want cell A1, and then I hit enter, and it says, okay, that term is 4. Now I could keep doing that, I could keep going equals 3 plus, click on the previous term, but the spreadsheet has the ability to recognize that I always want the previous term. So instead what I do here is I click, let's see, Fen, did I miss the hangout? Okay, so she missed the invite, let's invite her again, hang on a sec. And okay, can I just click and reply to her? Just resent. Okay, so again, if I click here, it says, hey, you're adding 3 to the previous term. So what I do is click back at it, and then I grab the autofill button. I click and drag it down. Hi, Fen.
Hi, Mr. Parker. Did I miss you on Hangout?
For some reason, that first invitation must not have gotten to you. I don't know what went wrong.
Oh, okay.
But we got you now. Can you see my screen okay?
Yes.
Okay. So although it copied the formula 3 plus A1, when it pasted it, it automatically changed to the appropriate row each time. I copied it down 1, it added 1 to the reference to the row. That's called relative cell referencing in a spreadsheet. Okay? And they're built to do that. So super easy. Anytime you have a recursive formula, spreadsheet does it in 2 steps. So we'll do another example of that in a minute. Explicit formula means, if I want to get the 100th term, I don't need to know the 99th and the 98th. I can just immediately jump to it. Recursive, you have to go step by step. So the explicit formula in this case is going to look something like A equals something times n plus or minus some other number. And I have to figure out what those 2 numbers are. I related this back to y equals mx plus b. So I have to figure out what's the slope, what's the y-intercept here. And there's a couple of different ways to go about it. Now remember, b is the y-intercept here, so that means it's the point 0b. So considering my table here, here n is 1. If I went back before n was 1, how would I go back on the other side of the table here? I would subtract 3 instead. So what's 1 minus 3? -2. So according to the table here, the b should be a -2. So I'll fill that in. Choose a different color. Oops. So I think that's going to be a -2. And then m is the slope. Can you tell what the slope is by looking at the table? It's 3. Yeah, that's what we're increasing by each time. So I believe the formula here is to get any a in the list, just take 3 times its position and then subtract 2. Anytime you make up a formula like that, you should double check that it works. For example, what would the 4th term in my list be down here? Yeah, add 3 to 7 and we get 10. Double check that over here. If n equals 4, then a is going to be 3 times 4 plus 2, or minus 2, sorry. And if I take 3 times 4, I get 12, minus 2, I get 10. So my formula does work. Nice thing about the explicit formula is I immediately can get to the 100th or the 99th term. It's a little more work to come up with the explicit formula, but it's a little easier to use once I have it. Okay. All right, so that's linear models. Then we started talking about exponential models toward the end of class the other day. And exponential models, like linear, could either be recursive or explicit. So example of an exponential pattern could be, let's suppose I had 3, and then 6, and then 12. Can somebody predict what the 4th number is going to be? 24. So we're doubling to get the next one, and then 48, and so on. So recursively, let's call this sequence B. The first term is 3. I started at 3. And then what do I do to get the next term? I'm multiplying by 2. So then to get any additional term, we call those the BNs, I take 2 times the previous term. Previous term is always letter sub n minus 1. So all that says is, like we did up here, multiply by 2 to get the next term. Multiply by 2, multiply by 2, multiply by 2. All right, to turn this into an explicit formula, what we have to do is just kind of shorten the repeated multiplication. And the trick there was, what does repeated multiplication mean in math? It'd be an exponent, right? Yeah, so if I want to end up with over here, see, that's the first, that's the second, that's the third, that's the fourth, that's the fifth. That 5th term right there, all I have to do is make a note that to get the 4th term, I start at 3, and then I need to multiply by 2. Or sorry, that's the 5th term I want. To get to the 5th term, 1, 2, 3, 4 2's to get there. So my claim is that the 5th term is 3 times 2 to the 4th power. And I can kind of project, like double check what is true for the 4th term. The 4th term, to get there, we start at 3 and we multiply a bunch of 2's. How many 2's did we have to multiply to get to the 4th term? 1, 2, 3. So it would be 3 times 2 to the third power. Double check. 2 to the third power is 8. 8 times 3 is 24. Yeah, that works. Notice the relationship between the position I'm at and the power I'm using. So if I wanted to generalize this explicit formula to the any value for n, doesn't matter if it's 4 or 5 or 100, I would take 3 times 2 to what power? Almost. So what's the relationship between this number and that number, this number and that number? It's always 1 less. Yeah, n minus 1. So it'd be 3 times 2 to the n minus 1 is the way that one works. And recursive formulas, spreadsheets are designed to do those easily. Explicit formulas, although we like them better as humans on paper, it's a little more work to make the calculator use an explicit formula because the explicit formula needs to know what n is. When we do it recursively, I'm just generating this list. Although I can count out what n is, I don't actually need to know it on the screen. So if I wanted to make the computer do this, I could either go recursively or explicitly. I'll do it both ways. Then we'll look at some story problems. So let's see, this was a linear one. Let's label it. Over here, I'm going to do an exponential, and first I'm going to do it recursively. Let's see, we were starting at 3, right? And then we had to double to get the next term. So I hit my equals, I type 2 times, and then I just click on the previous term. Then all I have to do is go back to that formula, point to the bottom right corner and fill it down, and it will automatically generate that list of numbers. So on a spreadsheet, recursive things are super fast and easy. Just takes a couple of steps. If I want to do it explicitly, that would involve telling the computer about this formula down here, which means I have to point out where the n's live. Well, n is how I count, 1, 2, 3, 4. Do I have a list of numbers on the screen that go 1, 2, 3, 4? Answer is no, I don't. So in order to use the explicit formula on a spreadsheet, you also have to type your values for n. So I would have to have a column here that goes 1, then 2, then 3, then 4, then 5, then 6, and so on. Once I have those, then I can tell it the formula. The formula was equals 3 times 2. Anybody know how to get a computer to do an exponent? It's the caret symbol, which is Shift 6 on the keyboard. That little hat's called a caret. And then I tell it where n is, and n is located right next door here. Now, and then I can use that to just fill down, and it should generate the numbers. Oops, what happened there? Oh, did I do my power right? I'm saying the power is n. What should the power be? N minus 1, okay. All right, so let's see. Let's try and fix that. So should I just be able to go here and type a minus 1? I don't know, let's try it. 5, is that the right answer? Oh shit, that's wrong. Okay, what did I do wrong in my formula? Yes, when we write on paper, we write this little subscripted thing up there. It's implied you have to do that before you can use it as a power. First step is to take away 1, then you can use it as a power. To tell the computer to do the same thing, I have to put the power in parentheses. So anytime your power is complicated, it's got to go in parentheses. So I put it in parentheses and hit enter. Now it should compute the numbers correctly. So here's so one problem with the explicit formula is I have to have another cell where n is located. However, here I generated all these extra numbers. I had to do that for the explicit one, otherwise there's no other way to get them. But watch this. I'm going to delete those guys there. This formula is set up to always look here for n. So I could just say, hey, n is 100 or 10. And it will automatically recalculate based on n equals 10, which is nice. So there are benefits to doing the explicit formula, even though it's a couple of extra steps on a spreadsheet. So if the homework said, what is the 100th term? And I know the explicit formula, I can just type it in and it's a gigantic number. Let's see if I make that bigger, will it show me? No, it's too big to show. 30 places. Okay. So what's the problem with exponential growth? It grows awfully fast. And we'll look at that in a minute too. That number is too big, but it's correct. All right. Common places we see linear or exponential growth. Population growth and money. All right, so let's start with a population of bacteria. We were talking about that the other day. Bacteria. And let's suppose there's a starting population of 100 organisms. And let's suppose that these bacteria increase by 50% every hour. Okay, so every hour, there's a 50% more than I had before. And for now, let's just make believe they don't die either. So we keep getting more and more bacteria. The 50% here is known as a growth rate. And so I just want to take a look at what happens with this population. So let's make a table for it. Here we have time in hours. And we have bacteria. And usually when we talk about starting, that would be 0 is where we start. So at time 0, when we started looking, there were, how many did I say? 100. 100 bacteria. Now what I need to do next is I need to make this increase by 50%. Okay, so then I have to say, okay, what's 50% of 100? Well, that's 50, and then I have to add it on. So now I should have 150 bacteria in 1 hour. Okay, so just double check. The adding 50% means I have to take 0.5 times that 100, and then I have to add that 100 back on. And that's where that comes from. And we have to keep repeating that every hour. So at the moment, I have a recursive pattern. Add 50% more each time. Okay, so let's see. 50% of 150 is what? 75, so I have to add 75 to that, and that should give me 225. Again, the calculation that made that happen was to take 50% of the previous number, 150, and add it back on to that previous number. And then we just keep doing this. Let's do the third one. Take 50% of 225. I think that's 112 and a half. And I have to add it back onto that. That's going to give me, what's that? Okay. So add that on, that's going to give me what, 340, wait, 112, 339.5, is that right? What happens when you add that back on? 337, oh yeah, I can't add, 7.5, there we go, is my new amount. How did we get that? Same thing we just described. We take 50% of the previous number. and we add on the previous number. So a spreadsheet would make this much easier. Alternatively, I could try and shorten this formula. What's repetitive in this formula? There's a couple things. Okay, it's 50% every time. What else is repetitive? Plus the number, right? So if I algebraize this, I'm taking 50% of the previous number. We usually call the previous number a sub n minus 1, right? And I'm adding that on to the previous number, a sub n minus 1. Now, the n minus 1 is kind of an annoyance. How many people is that an annoyance to? Okay, it's algebra. I think it's beautiful, but it can be annoying. I could instead say I could call the previous term a. So I could say this is 0.5 a plus a. Can that be cleaned up algebraically? Okay, those are like terms, right? So what does that clean up to be? What's that? Nope. That would be a plus a. This is 0.5 a's plus 1a. How many a's do I have altogether? Nope. I would have 1.5a. Yeah, I have half an a and I have a whole a. How many a's do I have altogether? I have 1.5 a's. So this right here is really 1.5 times a, where I'm calling a the previous amount. So an easiest, let's double check this. Take the 225, multiply it by 1.5. What do you get? Whip out those calculators. What's 1.5 times 225? My claim, if my algebra is right, is it's 337.5. 225 times 1.5. Works out. Okay. So again, it's super important that you guys are always using your calculators, because I'm not always here to advise, right? So you need to be comfortable typing stuff in. So we have a shortcut now. So now to get the fourth number in my list, all I have to do is take that previous number, 337.5, and multiply it by 1.5, and that'll be my new number here. What's that turn out to be? 506 1/4. Now, we can't have 1/4 of a bacteria, so that's kind of weird, but we're going to hang on to the decimal for now anyway. So we would say, oh, we have about 506, right? Over here, we would say we have about 338 bacteria. Okay, we usually round up. Now, every time you have a growth, there's nothing special about 50%. If this was a 30% increase, guess what this multiplier would be instead? 1.3. Yeah. So the bottom line is, anytime you're given a growth rate, you can turn that growth rate into what's called a multiplying factor. By just adding 1 to it. So the multiplying factor here will be 150%, which is 1.5 as a decimal. And the although the growth rate, yeah, it's important. I need to know the growth rate, but it's the multiplying factor that's more important, because that gets me quickly from year to year, hour to hour, whatever, that multiplying factor. Be 109% or 1.09. Yeah, so just some examples of that, just for fun here. If we took a look at growth rates versus multiplying factors, if the growth rate was 50%, adding 1 to that means the multiplying factor is 1.5. Why 0.5? Because 50% is 0.5. Why the 1? Because we're always looking back at the original number, and the original number is always 100% of what you started with. Like AJ said, if it was 9%, well, 9% as a decimal is 0.09, so the multiplying factor must be 1.09. Now, sometimes growth is negative, though. So you can't have negative growth rates. Like depreciation, right? I bought a new car the other day. As soon as I drove off the lot, it lost money. Every year, it's worth less and less, right? So we could have a growth rate of negative 10%, which means Here I have 1 plus 50. Why plus 50? Because that's an increase. Why plus 9? Because it's an increase. So the multiplying factor for a decrease, guess what's going to happen? It's going to be 1 minus. Here, that came from 1 plus 0.5. So if I have a decreasing rate, that would be 1 minus 10%. So I would end up with 90% of what I had before. So if a car, depreciation rate about 10%, it's not too far off for your average new car. My car is going to be worth 90% of what it was the previous year every year. That's one way to do depreciation. Okay, so sometimes things increase, sometimes things decrease. Population. Do you think population is always increasing in a given place? Yeah, so I grew up in Rhode Island, and when I was in my early 20s, me and a whole bunch of people like me and retirees were leaving Rhode Island in flocks. And so the population was dropping. So when I was 19, the population was about 1 million people in Rhode Island. When I was 21, the population was under 1 million people because young people and old people were leaving the state. Old people went to Florida, young people went to find a job elsewhere because they didn't exist there. So it's possible to have negative growth rates and you can have positive growth rates. So we'll take a look at each one. Can anybody think of some other circumstances we might have a negative growth rate? Homes can depreciate. Yep, sometimes they appreciate, sometimes it depends on the market. That's a good example. Okay, other things? How about money? Is my dollar going to buy me the same amount of stuff next year that it's buying today? No, because there's inflation in the economy. Inflation means your cash is worth less later because everything else is worth more. So it could be maybe if appreciation is 10%, that means your dollar buys 10% less than it could before. So yeah, so next year your dollar today is only worth 90 cents. And the year after that, it would be 90% of 90%. What's 0.9 times 0.9? Almost 81. So that means it'd be about 80. So in 2 years, our dollar would be worth about 81% of what it's worth now. Now, inflation is not 10%. Typically, inflation's around 2-ish%. It's not that high. But still, over time, it adds up. Okay. Well, that is inflation, that the prices go up, and there's lots of reason that it happens. And I'm not an economist, so I'm not going to weigh in on those reasons. But there's a lot of them out there. Yeah. Right, and now it's like $2 or, yeah, right. Yeah, so let's look at this bacteria problem a little more. New page for it. So I'm going to just simplify the table a touch. Time versus bacteria. At time 0, we had 100 bacteria. And then we moved on to take that 100 times 1.5. That gave us 150. In the second hour, excuse me, didn't we take that 150 and multiply by 1.5? Because that's the multiplication factor. That gave us 225. Now just break this down a sec. Where did the 150 come from again? It took the 100 and multiplied by 1.5. So aren't I repeatedly multiplying by 1.5? Yeah. So another way I can write what's happening in this second hour here, oops, stop it, is I could say for the 2, starting with 100, multiply by 1.5, and then multiply by 1.5 again, because I need to get to that second position. Can I shorten 1.5 times 1.5? It'd be 1.5 to the second power. So in the second hour, I really have 100 times 1.5 to the second power. Just double check on your calculator. Do that calculation. Does it really come out to 225?
Yes.
Okay. All right. So it does work. So that means in the third year or third hour, I should have 100 times 1.5 to the third power. And every calculator does powers differently, so you got to get used to your calculator. So often I use Google as my calculator. Sometimes it's Google Sheets. Sometimes I just go to my browser here and type 100 times 1.5. How do I get a power again on a keyboard? Caret, which is shift 6. Oh, there it is. And then I say, give me the power 3. Google says, oh, you want 337.5, which we saw before. In this chapter and the next chapter, you're going to get really good at your calculator, or just use a spreadsheet all the time. So I could totally do this on the spreadsheet too, in a couple of different ways. Let's do a sheet for our bacteria. So either I could use the recursive one, or I could use the explicit formula. So here I have hours in one column and bacteria in the other. At 0 hours, I have 100 bacteria. So that was my starting point. 1 hour later, a couple of ways I can do it. I could say take 100 and multiply by 1.5. And then I could just repeat that process. And it will keep generating those numbers I need. Okay. How do I get the 0, 1 pattern to continue? Anybody? I could just add 1, yeah. So I could go here, go equals 0 plus 1. And notice I didn't type 0. I clicked on 0 where 0 was. Click back on the formula and fill it down. That works too. To get the explicit formula, which is the last thing that we figured out here, notice the time matches the power here. In our previous example, it didn't. It was 1 off. So I could just say equals 100 times, let's see, 1.5 is my base, raised to the power whatever hour I'm at. And that should generate the right numbers too. So we have a couple of ways to use the spreadsheets. Here I'm using the explicit formula. For these problems up there, I use the recursive formula. Sometimes one's easier than the other. Sometimes it depends on the question that you were asked. All right, let's do another example. Let's see. Let's do a depreciation problem, and then we'll take a look at what's called logistic growth. So let's say a car depreciates, oops, by 8% per year. Oops. So the 8%, is that a growth rate or is it a multiplying factor? It's a growth rate. Yeah, anytime you have something per year, per month, per day, per hour, that's always a rate. The per makes it a rate. To change it into a multiplying factor, we have to compare it to 100%. Now here, since I'm depreciating instead of appreciating, I'm losing from my base value. I'm losing 8%. So it's 100% minus 8%, 92%.
92.
Yeah, so 92% is my multiplying factor. Okay. So it's the multiplying factor that gets me from year to year or month to month or day to day, whatever I'm moving from. So here it's a multiplying factor for years. So I can build a table for this. Year versus the car value, or let's call it years. So when we start out, let's say we had a $15,000 car. After 1 year, it's going to be worth what percent of its original value? 92%. Yeah, so to get the answer, I just take my 15,000 and multiply by my 92% as a decimal, and out pops the actual value of the car after a year. What do we got? 19,800. 13,000. Oh yeah, oh yeah. Lost my eraser. There it is. Okay, thank you. And then we just keep repeatedly applying the 0.92. So if we take 0.92% of that, or sorry, 0.92 of that, what's the next one going to be? $12,696. Anybody else get that?
Mm-hmm.
Okay. Now, if I want to jump on down to like the 10th year, without repeatedly multiplying, I just consider how many times I need to multiply. I started at 15,000. I want to multiply by 0.92 a bunch of times. Oops. Well, in the first year, I had one multiplication. The second year led to a second multiplication. So altogether, how many multiplications are happening into the 10th year? 10 of them.
9.
No. Well, there'll be 10 of them here, because to get from 0 to 1, I had to do it. Then from get to 1 to 2, I had to do it again. So for example, this 12,696 is 15,000 times 0.92 to the power 2, because it's the second application of that depreciation. Each year gives me a new application.
Hi, how are you doing? It's up everybody through this invitational to your neighbors. It's an invitation to study the Bible.
Oh, okay. I'm online class, so I don't have time right now. Sorry.
All right, maybe we can come back some other time. That'd be all right.
That's fine. Thank you. All right, come. All right, calm down. Come on.